Okay. So in these classes, we are doing the most important topic, where you are getting introduced to non-linear behavior of different structural components. Okay. So we started with non-linear behavior of material, that is given by the stress strain curve. Then we discussed non-linear behavior of a section, which is given by moment curve. So we first talked about steel sections, and then we talked about RCC section. Okay, procedure is very similar. You are considering different strains. Okay, so any section, whether it is made of steel or concrete or composite or anything, you will assume a neutral axis, consider some strain either in compression or tension, then assuming Euler-Bernoulli hypothesis, you can complete the strain diagram. Then, knowing the stress strain curve of the material, you can plot the stress diagram. It may be linear, it may be non-linear, it may be parabolic, it may be constant, depending on the stress strain behavior of the material. So corresponding to each strain here, you have to read the value of stress here. Okay, and that stress you are plotting. Once you know the stress strain diagram, the stress variation, you can calculate compressive force and tensile force. Okay, and this compressive force and tensile force you can put in the equation of equilibrium. If it is beam, then P may be equal to 0. If it is column, axial force is also there, then P is non-zero. Okay, so you can calculate C minus T equal to P. If it is satisfied, then this depth of neutral axis, which you have assumed, is okay. Otherwise, you have to change it. And then, if it is satisfied, you can calculate the moment of this section at this strain, okay, about the centroidal axis. If the axial force is 0, then it doesn't matter, the axis doesn't matter. But otherwise, you have to take the moment about the centroidal axis. So this is our centroidal axis of the section. And this is our neutral axis. Neutral axis is where we have zero strain. Okay, the strain is changing the sign. Centroidal axis is just at the center of the section. So moments, if axial force is non-zero, then we have to calculate about centroidal axis. In fact, you can make it a practice to calculate about centroidal axis in all the cases. In case of P equal to 0, it will not matter. The axis will not make any difference on the computed value. Okay, so you can get moment then, and curvature you can get from the strain diagram. So this angle is the curvature. You can plot the moment curvature for any section under 0 or non-zero axial force. Is this clear up to this point? So if you look in the assignment which I have given you, in the beginning I have given you only some of the sections. Okay, the initial few questions, those will give you different types of sections. The first one is steel. Okay, only thing is it is a hollow section. So what difference it will make? That by calculating the forces of the stress distribution, it will remain same. Okay, the difference will be that when you are calculating compressive and tensile forces, you have to consider the area present there, which is subjected to this stress. So calculation of C and T will change. Rest of the procedure will remain same. Then question number 2, it is RCC section, but confinement is also there. So what effect confinement will have? At my, or let us say my dash. First we are calculating my dash. What effect it will have on my dash? Up to my dash? Very little. Okay. Because cover will also be present and the stress strain curve will also be closed. It won't be same because it's started changing slightly before that. Okay. But there will be little difference. So if you ignore, okay, you consider the unconfined stress strain curve of concrete, okay, and include cover also, it won't be in error, much error. Okay. So you can simplify that. So my dash you can obtain like this. But what about mu? How you will compute mu? What will happen at mu? Ultimate point. The cover concrete will fall. Okay. So the cover concrete will spot. Only core will be remaining, and core will have confined stress strain curve. So you have to take the stress strain curve for confined concrete, and one of the models for that is Mander's model, which we have discussed in the class. You can use that model to plot the stress strain curve and use that stress strain curve to get mu. Okay, and the corresponding value. So like that you can plot this moment curvature curve. In general, the moment curvature curve will be something like this. This is generalized curve. Okay. You have seen in some cases it remains flat, some cases it may go down, some cases it may go little up also. In case of steel section, the initial portion was a straight line. Okay. In case of RCC, till cracking, the stiffness was very large. Then it started reducing after cracking. Okay. So like that, the shape will change from section to section, material to material. Okay, but this general shape we can plot that it is a curve. So in general, the moment curvature curve will be curvilinear. Okay, and to simplify the calculations, we represent it by equivalent bilinear curve. And what is our equivalent bilinear curve? We represent it by two lines in such a way that the area under these two lines is same. Okay, and this point corresponds to m by dash, and this is phi u, and this is so just knowing 2 points, you can plot the bilinear, not the actual curve, but you can plot the bilinear. You need only these 2 points. You agree? If you know these 2 points, you can plot the equivalent bilinear curve. Okay?
So, but in case of concrete, how do we calculate these?
How do we get?
How do we get that E point? We can get that m by dash.
M by dash you can get, but how to get m by?
Yes.
And phi by. Okay. In case of steel, you have seen that m by is almost equal to mu. So in case of steel section, you can take m by is equal to mu. But in case of RCC, m by may not be equal to mu. So in that case, how to get m by? Based on analysis of a number of sections, 2 criteria are given. One is what Priestley has shown. Priestley has suggested that m by dash can be taken as 0.75 times m1. Okay. So if you know m by dash, how to get m by? Okay, for RCC section. Okay, in Caltrans, oh, m by is considered as m 0.04. What is this m 0.04? The moment capacity at concrete strain of 0.4%. That is also the nominal capacity which we calculate in our limit state analysis. In limit state analysis or ultimate load analysis, we consider corresponding to 0.0035. If you consider it 0.0035, 0.004, there won't be much difference in the capacity. So what you are obtaining in the ultimate load or limit state method without factor of safety and considering expected strength, same value you can treat as M1, and the approximate ratio is 0.75. Any of these two relationships you can use. First one is much easier, so usually you will use that. So if you know m by dash, you can get m by using this simple relationship. Then you can complete the full curve. Okay, so all of you can do up to question number 3. Question number 1, 2, 3. Anything you want to know?
We are taking the slope of initial state release.
Right. This slope of M5 curve, this is EI factor, and you can see from this slope it is m by dash divided by 5 by dash, because this line is passing through first unit point. So once you know m by dash and 5 by dash, you can calculate EI factor. In case of steel sections, you have seen it will be same as the gross moment of inertia. In case of solid section, it will be BDQ by 12. In case of hollow section, you can calculate. Okay, so are you comfortable up to question number 3? I will come to that. Yes? Ask. We will talk about that also. Shear deformation we have discussed, but Q delta curve we will discuss. Shear deformation we have discussed in the last question. What happens due to shear deformation? Additional deformation comes. And how much is that additional deformation? You can calculate shear stress. From shear stress you can calculate shear strain. Shear strain multiplied by length will give you the deformation, shear deformation. So that much shear deformation will be added. So in case of a cantilever subjected to a point load at the tip, how much will be the shear deformation? Yes? QL by? QL by G into A. Okay. So QL by GA, that will be our shear deformation. How much is this A? Is it same as the area of cross section? Shear. So what is the shear area? Let us say you are doing this hollow section. Here, how much is the shear area? Question number 1 you are doing, so how much will be the shear area? In case of flame sections, how much is the shear area? Area of the web. So web only is effective in shear, the flanges are not. So just to calculate the web area, that will be shear area. That we will add. Okay? Only thing, how to plot Q versus delta. That we will take up now. So let's consider this cantilever as vertical. Doesn't matter. I have applied the force Q. Okay. It will be subjected to a bending moment. A linear bending moment. Okay. How will be the curvature diagram? Let us say the section has not yet yielded. So how will be the curvature diagram? Can you plot the curvature diagram? From this, the curvature depends on the moment. Initially, you can assume it to be linear up to limit. Okay. So before yield, if the applied force is small, okay. So before yield, how will be the curvature diagram? Variation of curvature along the line. You know the variation of the moment. So moment is increasing towards the support. It's linearly increasing. So how the curvature will increase? Linear relationship between the two. So that will also increase linearly. What will be the value here of the curvature? QL over EI. Agreed? If this is the curvature diagram, can you calculate displacement? You know the relationship between curvature and slope? What is the relationship between curvature and slope? It is integral. Okay. So slope is integral of the curvature. So can you plot the slope diagram? And if you have to get displacement, then what you have to do? Double integrate. Geometrically, how do we get double integration? Slope we get by considering area. Okay. So if you want to calculate slope anywhere here, let us say at this point, what you have to do? You have to simply consider this much area. That will give you the slope. Suppose I want to calculate displacement here. How can I calculate? So you can try this when you take second moment, or sorry, double integral when you do, it becomes moment of that area. So moment of area about this point, okay, this will give you the displacement. So the delta at the tip How much will be that? Let us say this is 5. So how much will be delta in terms of 5? We have to take the moment of this whole area about the tip. Please do that. Area is 1 upon 2 into L into 5. Okay. Let me call it 5 naught just to differentiate it from the variable curvature. So curvature here is 5 naught. Okay. Into the lever arm. How much is the lever arm? So this becomes okay. 5 naught is M over EI or QL over EI. So this also becomes QLQ over EI. Okay. So this is okay till yield occurs. So in the same manner you can calculate delta y. In case of delta y you have to simply substitute phi naught as phi y, and that is my L square 3EL factor. Agree? If you increase this further and the moment here, what will happen when yielding occurs? What will happen to the moment? Will the moment still remain linear or variation of moment along the height? When yielding has occurred at the base, here, yielding has occurred, what will happen to the moment? Moment will remain constant?
Reduce and get constant.
Hmm?
Reduce and get constant.
It will?
Reduce and get constant.
It will reduce and get, why it will reduce?
No, it will reduce. Slope will reduce.
You mean it will be like this? Everybody agrees?
So moment is force into the current.
Yes. It will be linear. So you are saying that the moment will be actually this only. Moment diagram will be like this only. So what do you think? So I told you that 3 conditions are to be always satisfied. What are those 3 conditions? Whether your structure is linear, non-linear, elastic, static, dynamic, whatever. 3 conditions are to be always satisfied. What are those 3 conditions? Equilibrium. Okay. So if the moment is constant here, equilibrium cannot be satisfied. So for equilibrium to be satisfied, this has to be always Q into L, even if Q is greater than Qy. Even then, it has to be satisfied. So moment will be increasing linearly only, even if it has become non-linear. What will happen to the curvature? Plot curvature. When moment is more than my. look at the moment curvature diagram which we have already plotted. Keeping that in mind, plot the variation of curvature along the length of this cantilever. This is curvature. So what happens when moment exceeds my, the curvature does not increase beyond that. What happens to the curvature, variation of curvature with moment after my? Does curvature becomes constant after mi? No. So okay. So how much is that in you show? Look at the diagram which you have already plotted. Amplified diagram you have already plotted. Look, what is it? Here. What is this? This amplified diagram only, no? So what happens? M is increasing like this. Okay, so what is happening with phi? Only thing is that in this case the M is increasing upward. In our case M is increasing downward. So what you have to do? You have to simply rotate it. You rotate it about this axis. Rather than increasing upward, our moment is increasing downward. That's it. So then you will get curvature on this axis. So invert it. What you are going to get? Plot. How will it look like? Yes. Capacity moment is what? Capacity moment is when the capacity of my section is reached. But how you are going to obtain the capacity? You will go on applying Q to this apply Q. This is capacity of the section. But when you plot capacity of the section in terms of variable moments, then how the variable moment will be applied on the section? Yes, applied. Okay, so moment cannot be more than its capacity. See, three conditions it satisfies: equilibrium, compatibility, and constitutive law. Constitutive law is that ultimate moment when it will reach, it will break. That is constitutive law. No material can take, no section can take more force than its capacity. Okay, so if it is more than its capacity, it will fail. So this moment, if this Q is greater than QU, it will definitely fail. But in between, what will happen? It has not exceeded QU yet. Okay, but has exceeded Q1. So what is going to happen to curvature? That same diagram which we have plotted, we have to just rotate it about the horizontal axis. you flip it vertically, then what you get? This type of diagram, isn't it? So this is our variation of curvature. And this curvature, if Q reaches QU, it will be equal to 5. You agree up to this point or not? If the moment curvature curve is of strain hardening type. Strain hardening type means what? That this is increasing. Then you will get this type of curve. Suppose it is not of strain hardening type, it is of this type. Then what will happen? Then what will happen? As I go on increasing Q, what will happen to the curvature? It will increase till you reach at the peak. After that, what will happen? Will it fail? You have to reduce the Q. Okay? So, the curvature or the moment or the force will go on increasing with curvature till this point. Okay. After that, you have to reduce the Q. So what I have plotted here, this is the case of strain hardening time. So where the moment increases continuously, okay, although the increase may be very small, but it increases continuously till that type of curve if you plot, then you will get it. Otherwise, this will be up to the peak point. If it is of a strain softening type, then whatever is the peak point, up to that you will get it. Okay, you agree? No? Where is the difficulty? What you are not able to digest?
When we plot this entire diagram, after a particular point, the value.
Suppose you have to plot this amphi diagram experimentally. I give you a beam, cantilever beam. You have to plot that amphi diagram experimentally. How you will plot? You can't take section. You can't take a slice of the section and apply amphi. Of course you can't do it. You will be doing it on beam. Okay, so there is a cantilever beam. I want to plot amphi curve. How can I plot? Yes? We will apply the load and measure the deflection. Okay, but I am not interested in deflection. I am interested in curvature. Moment curvature diagram. Then you have to measure curvature. Measuring deflection alone at the tip will not be enough. You have to measure the displacement along the full length at every point. Okay, and then take the second derivative in the vicinity of the support. That will give you the curvature. But how you are going to vary the moment? Because you have to obtain moment and curvature at different points. So how you are going to vary the moment? You are going to increase Q only at the tip. You will go on increasing the load. You can calculate the moment. You can measure the displacement. Then from the measured displacement you can calculate the curvature. You can plot it. Okay. So at this point, or let me draw another orientation. At this point, you are measuring the curvature, okay, and you are increasing the Q. So you are going on increasing the M, you are measuring the curvature, it will go like this. You agree? Now, what will happen at this section? This section and this section?
Less curvature that kind of is.
So actually, it is nothing, but you can see these are the different values of m. So you need not to measure at different points. What you need to do, you apply just this q equal to qu ultimate. Then moment will be automatically varying in the same measurement. You can see that moment is varying from 0 to mu, isn't it? And you measure the curvature here, 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 here. That will give you the same line. So at one section, you are measuring the curvature under increasing moment, or at different sections under a given load, because my moment is increasing linearly. If it was UDL, then I can't do this. Okay, then linear relationship will not be there. Then I have to calculate moment considering the distribution of the load. But if it is concentrated load like this, then I have an advantage that the moment varies linearly. And this acts like my y-axis. At y-axis, what is happening? We are increasing the moment linearly now. That's how the moment is increasing. So I have to just rotate it at 90 degree. You agree? So what I am getting at different locations, that phi is the same as varying with increasing moment, because the moment is increasing linearly. So whether you are plotting it on an axis or you are measuring along the length of the cantilever beam, this is one of the same thing. Okay. So moment, irrespective of capacity is there or not there, or it has yielded or not yielded, moment will always vary linearly. It will be simply q into distance. It doesn't change. If your structure does not have that much capacity, it will fail. If it has that much capacity, it will sustain. But the applied moment cannot change its nature because your section is not able to take that much. It will always increase linearly. Equilibrium has to be satisfied. So the moment which is applied will be calculated using equilibrium condition. Equilibrium has to be satisfied at all the points, at all the instants of time. Okay? So now you agree with this curvature? That this will be the curvature diagram? No, I have to calculate displacement now in this case at the top. What I have to do? I have again to double integrate. Okay. Can you double integrate this? Here it was very easy. You have integrated. But can you double integrate this? You can, provided you know the equation. Okay. And if that equation is of the form which you can easily integrate. Okay. Otherwise you have to integrate it numerically. If you know the value, you can do it numerically. But if I convert this into equivalent bilinear, how? If I convert this into equivalent bilinear like I have done here, then it becomes very easy. Then integration, double integration becomes very easy. And now you understand why we are converting it into equivalent bilinear. To make this calculation simple, rather than computing the whole m phi curve, we had computed only 2 points on that m phi curve. Okay? If I want to calculate the displacement at that tip, I have to double integrate this whole area under this curve, which is quite complex. But if I convert it into equivalent bilinear like this, it becomes easy. How? That first we convert into equivalent bilinear and then we represent it by another where we consider this as going up to here and this we consider as phi y. Okay, you can see that it is slightly higher than the previous one. Okay, previous one, the phi y was this. Remember, this is our x-axis, so this was phi y. Always keep this in mind. A slight change is there where I am considering this length. Actually, I should have considered length up to this much only for integration. Okay, but I am considering the full length. So this is slightly higher. Let's call this as phi y. Okay, and then in place of this curve and inclined curve, I will take a rectangular curve, a uniform variation. Okay, and this length on which I get this uniform variation, this I call LP. Let me draw this more clearly. I will emphasize on this portion. Okay, so we have first represented it by equivalent bilinear, then what I am doing? I am representing it by a triangle and a rectangle. So this was phi y, this is phi u, okay, and this difference we call phi p, plastic curvature, and the dimension of this rectangle, this we call L. Now perhaps it will be clear. What is this point? This is phi y dash. Okay, so this much length of the column has yielded beyond where the yielding starts at phi y dash. Look here, where this moment is reaching m by dash. Beyond that, the steel here, this much steel is yielding, and the strain in this steel is increasing. Here it is epsilon y, and here it is epsilon u. So beyond that, it is less than epsilon y. So the steel here is elastic. Steel has started yielding here, and then the strain goes on increasing, and at the support it becomes epsilon u, and there it is just at the verge of rupture. That's where the rupture will take place. So this much length is yielding. Okay. Now the length which I have represented by LP, is it more than this or less than this? Or same? This is the yield length. You can see that this is going to be smaller than that. Okay, because I am considering uniform variation of curvature, whereas it is curved in this length. Okay, so this is definitely going to be less than that. Okay. and this LP we call plastic hinge length. Okay, so this we call plastic hinge length. Plastic hinge length is coming from the equivalent moment curvature curve. So equivalent moment curvature curve, which was actually curvilinear, then it was bilinear. I have converted that bilinear into a triangle portion and a constant portion. Okay, so when I convert this into this constant portion, then this length of this constant curvature, that is LP, the length of the beam in which I can assume the constant curvature. Let us look it here, then perhaps you will be in a better position. I have plotted moment here. If I plot curvature, how the curvature will vary? Like this. Okay, I have represented this by one is triangular and another is this rectangle. Area is not same. What has to be same in this case? The moment of area. Okay, how this equivalence will be obtained? This is not obtained from area being equal. This will come from moment of area of the two curves being equal. Why moment of area? Because we are interested in displacement calculation, and displacement is given by moment of area or second integral of the curvature curve. So this length here, let me use another curve. So this length is the plastic hinge length. Actual yielding is occurring in this much. So it is not the length in which steel has yielded, or if it was a steel section, then in which the extreme fiber has yielded. It is not that length. It is a notional length. Okay, and that notional length we obtained in such a way that the displacement at the tip remains same, or the moment of the two area diagrams remains same. The moment of this diagram and this equivalent triangle and rectangle remains same. Yes.
Each plastic hinge length is similar to the length of plastic zone.
No. Plastic, that's what I told. Plastic zone is this, what I have shown by this yellow color. That is the plastic zone. So this much, in this much zone, the steel is going to yield, or it will get plastified. Okay. Although the plastic strain may not be same. Plastic strain is what? Okay. So here just yield has started. So here epsilon is equal to epsilon y. So plastic strain is 0, and then the plastic strain goes on increasing.
Just for example, a section. First we have to yield to reach up to the yield. Means upper or bottom towards the yield stretch. Then increasing the load, then yielding to the bottom fiber reach towards. After that, when we reach to the ultimate point, this plastic is formed, and the plastic length is less as compared to the yielding length of the fiber. That means.
You can, I have given an example of a RCC section. You can also think of a steel beam. Suppose this is a steel beam, rectangular steel beam. What will happen here? The moment will be always like this. At this section where this is equal to my, what is the strain diagram? The strain diagram is this. Okay, here it is epsilon y. Or let me plot a stress diagram, that will be more instructive. So if I plot Fy, what will happen here? What will happen here? The whole section okay. If I plot the plastified zone which has plastified, how that is increasing? Here there is no plastic zone. Okay, so let me use another color. So the plastic zone will be so this much zone has plastic. Here the top fiber just started yielding. Okay, and here almost whole section has it. So the zone in which plastification of steel has occurred, that will be given by this point, where up to which point the stress is constant.
Sir,
Yes.
please explain the difference. Like here we need like from starting things to then first and then plastic zone.
LP I have not shown here. LP is not there. LP is coming from the equivalence of displacement. It is not physical length. It is a notional length which is coming from mathematics
Just
by equating the displacement.
Just for our calculation.
Just for our calculation.
It doesn't any.
It is not this length which has plastified. That's what I want to make clear. That the LP is not the length which has plastified. Okay? LP is a notional length which we have defined for the purpose of our calculation, so that we are able to calculate the displacement. Any point up to this point? Yes. See, if area is equal, then the slope will be same. Slope will be equal. But we don't want the slope to be equal. We want the displacement to be equal, so that our calculated displacement is correct. So the moment of these two areas should be equal. Yes. Wherever the moment is maximum, naturally there the failure will occur. Maximum curvature is going to occur here at this point. So actually curvature is varying. So it is not, we can't define a point at which the increase occurs. See, if it was rotating about a point, all the curvature was concentrated at a point. Hinge means what? What is the difference? Let's say I have two types of beam. One beam is this, another beam if I ask you to plot the curvature diagram for the two, let us say it has some friction, so this load is not zero, okay, it has some friction. That's how you define plastic hinges. You have defined plastic hinges in your feeders, that plastic hinges are like corroded hinges, where you have to apply some force, okay, some friction is there. So to overcome that friction you have to apply force, but once that friction is overcome, then it moves free. Okay, so if I ask you to plot first the deformed shape, then slope, and then curvature in these two cases, then you will be able to understand. Please do that. Plot moment, displacement, okay, slope and curvature in these two cases along the line. So plot the moment along the line. Let me tell you, moment will be linear in both the cases. Why? Because moment will be always following equilibrium. So moment has to be there. Now can you plot the displacement? How the deformed shape will look like? In first case, you have already done. At this point, the slope will be 0 and the displacement will be 0. But curvature will not be 0. Curvature will be maximum and it is going to deform like this. What will happen here? So, up till this point, there will be no deformation, and beyond that, it will deform in a straight line. Plot slope and curvature. What is this? So, but don't follow. Intentionally, I have found this portion. So, what will happen to the slope in that portion? So, here it is quite easy to plot the slope. Here to here it is constant, and then it becomes 0. So this is slope. How the slope is varying here? whatever you believe. So, how do we do it? Tangent of this curve. Tangent of this curve is it linearly or constant or what? Or if you want that idea from there, until unless you have idea. But you can also see, let's plot the curvature first. In this case, you know the relationship between curvature and moment. Curvature and moment are proportional. So if moment is linear, if it is elastic, that case we are considering. So this will be our curvature. Slope is integral of this. So can integral of this be linear? How will it look like? Integral of a triangle, can't you do that? You can simply write an equation and integrate it. If you can write phi at any x here, distance, let us say from here, x distance. What is phi x? Let me call this as phi naught. So how much is that? If I want to write it in terms of x, this is L. So at L it is 0, and at 0 it is equal to phi naught. So phi x is nothing but phi naught. You agree? Integrate it and plot. How will it look like? One thing is clear, that it will be parabolic. All of you agree? Integral of linear is going to be parabolic. Only thing you have to judge is that whether it will be like this or it will be like this. Will it be of first type or second type? Second type. Should we vote? First type. Okay. One is this bending moment diagram. Take another curvature which is like this. Suppose curvature was like this. Then how it would have some type?
First.
How do you say that in first case it will look like the first type, and in the second case the integral will look in the second type? In both the cases, you mean in this case and this case it will be similar? First type?
Sorry, in the second one, the value at x equal to L is 0, so the slope should be 0.
It is slope is 0 in both the cases. Here also it is
At
0.
this
It is
end,
not deformed shape.
The slope should be 0 at this end, sir.
Here, at x equal to 0. Why slope should be 0 in a cantilever at the free end? Slope at the free end is not 0. You have already plotted deformed shape. So is the slope 0 here? Actually the slope is maximum, not 0. Yes.
Like in second curve, as we are moving from left to right, the slope is decreasing, and that is the anterior of the below curve. So, like when we are moving, the slope is decreasing, and in the below.
Slope is increasing in both the cases. In first also the slope is increasing, in the second also the slope is increasing. Actually the space was less, so my drawing
In the
is.
second one, slope is decreasing.
Slope is decreasing. This is plotting slope, not the deformed shape. I am plotting theta itself. So theta is increasing. This is not the deformed shape. Deformed shape is this. So don't get confused that my beam is deforming like this. This is plot of the slope of the beam. So slope is increasing in both the cases.
Slope of the curvature is equal to rate of change of slope of the curvature. Slope of the rate of change.
Rate of change of slope. Okay, that you have to see. So what is slope? Slope is first area of the curvature diagram. So in a given length, suppose you take unit length here and unit length here, which is causing more change. So the rate of change of slope will be higher near the support and it will be lower near the tip. Agree? So which shape then? Second shape. Okay, so this is the theta diagram. So here curvature I have plotted first and then I have plotted theta. Here theta I have given. Can you plot curvature? Here you have integrated curvature to get theta. Here theta is there differentiated. How will it look like? Plot it. Just a straight line is saying straight line is not enough. A straight line can be vertical, a straight line can be horizontal, a straight line can be inclined. So how the curvature? Horizontal? Like this? You mean curvature is constant? Vertical. That means curvature is infinite everywhere. Can't you plot slope of this line? There is no slope. You agree there is no slope? There is constant slope. What is slope of this line? Theta. What is slope of this line? So there are only two types of lines. Here also it is 0. Just now you said that it has theta equal to 90 degree.
Member has not
Member has not?
just it has rotated around one.
If it has not banded, okay, this member has not bent anywhere, then how can you have slope? How can you have displacement?
Then theta is then joint. And whatever we are plotting theta is the slope of the deflected curve.
Wherever it is, you plot it. I want to only see the plot. So the plot will be that it will be, let me use another color. It will be 0 here, it will be 0 here, but here there will be very large curvature. Dirac delta function. So what does that mean? What point I wanted to convey you? Wherever hinge is, all the curvature is concentrated there. So now go reverse. Where the plastic hinge is, where we have concentrated curvature. So in our case, for our beam, where should be the hinge? Should it be at this face? Should it be here? Where? Where it should be? It should be at the center of this concentrator, at a distance of LP by 2. That's where we can assume our plastic hinge. All this is notional. Okay. In reality, the whole of this steel is yielding, and yielding is occurring like this. There is no single point about which the bending is taking place, like in a hinge. We are representing it by an idealized member, an idealized beam, something like this. Okay, so where should I assume it? At the center of LP. So at LP by 2, I can consider the plastic hinge. Now imagine this, that here I am taking a rigid beam. Suppose this is a flexible beam. Then what will happen? Here there will be hardly any deformation. There will be some rotation here. Okay, and then it will deform. I have exaggerated just to so if it was rigid like here, this you can say theta at the hinge. Whatever theta is occurring, that is occurring at the hinge. Okay. Here we have a plastic hinge. Okay. And the rotation is not only occurring at this plastic hinge, it is also occurring in the length of the member. So this, if this hinge was not there, this member would have deformed like this. But because hinge is there, then what will happen? It will have a plastic rotation here. So there will be a plastic rotation, and then this will deform. So this we call theta P. Okay, and then whatever is additional, that is theta Y. Okay, and this theta Y, we have to define a particular fashion, because what you see here, theta is changing, theta is not same. So which theta I should call theta Y? Where should I take this theta? So for that we use what we call chord rotation. In chord rotation, we join this point by this point, and then this angle, this was theta P, this angle is theta Y. Or chord rotation. This we call chord rotation. Why chord rotation? Because it is the rotation of the chord. If I say rotation of member, if I ask you what is the rotation of cantilever, it doesn't convey anything, because it's changing, the slope is changing, it is not same. So I can't define it by one quantity. Okay, so this theta Y, or the chord rotation, Here theta we define as delta divided by L, and theta y as delta y by L minus LP by 2, isn't it? Although this LP is small, LP by 2 will be further small, so we take it as delta y by L. Yes.
Obviously, if you increase the load greater than PV, the plastic is strong. The member will be strong and be able to transfer the load.
Right. So this portion of the member which has yielded, this will not be, but the remaining portion can still take the moment which is coming, because moment will also be varying. Okay. So the moment will be here, where we have plotted moment here. So this moment is varying. So till this section, it is elastic. It is less than my dash. So till this section, it is elastic. Beyond that, some inelasticity comes. We have simplified it. How we have simplified? That we assume that this triangle is representing the elastic portion. So we assume it to remain elastic right up to the center of the hinge. And then we add into it this plastic portion. So all the plasticity we have lumped at one point. Okay, and we have assigned a length of LP to that. Okay, so that's why we also call it lumped plastic hinge. 3 words. Just now we have seen what is behavior of a hinge. What does hinge do? Hinge concentrates curvature. So curvature is concentrated at hinge. That's the characteristic of hinge we have seen. What is meant by plastic? Plastic means the deformations beyond inelastic. So it is not a physical hinge. Okay, like the screw I have drawn, it's not that type of hinge. It is occurring because of the plasticity of the metal, because of the yielding of the material, because of the plastic flow in the material. Okay, actually it is not occurring at one point or even in this plastic hinge length, it is occurring in this yellow length, isn't it? Because actually this length has yielded. So actually this additional plastic curvature is occurring over whole of this length. But what I have done, I have assumed it to be concentrated only in length LP. Okay. Up to this point, are you with me? Think if any angle, any question is not clear to you, you ask. That will help others also in understanding. Yes.
Chord rotation.
Chord rotation. Okay. Let us take example of this cantilever itself. Suppose I ask you, what is rotation of this beam? What will be your answer? Under this load Q, it has not yielded yet. It is still elastic.
I can't see because we have to define one section of any point.
So you have to say where. If I ask you, tell me the rotation, your question will be where. So to take care of that question, we define chord rotation. So when it deforms, it makes a curve. I draw chord to that curve. So the chord to that curve is this. And then I take the rotation of this chord with respect to the original position. So this theta is my chord rotation. and theta is not equal to because that is varying. So this chord rotation is not slow. Okay, it is rotation of the chord. And actually it is representing displacement. It is nothing but equal to delta by L. So you can see that theta is actually representing displacement. So chord rotation is actually a measure of displacement, not measure of flow. Okay, so that's why we define chord rotation, because using this we can quantify or we can represent the displacement. Okay, now let us take the case of a hinge. So the rotation which is occurring here, what will be that rotation? That rotation will also be chord rotation. So this theta p which is occurring, this is adding to chord rotation. So when I have to combine theta with theta p, both should be defined in the same manner. So both are chord rotation. So when I am defining the rotation at the hinge, that is also chord rotation. So to combine some rotation with that, I should have chord rotation only. So that's why we define chord rotation. And in our calculations here, we will be using chord rotation.
So when theta 1 equal to delta y of L minus LP by 2.
Okay, because this length is LP by 2 and this length is L. So how much is this?
Why is it LP by 2?
Because we have considered this plastic hinge at the center of LP. We have considered this hinge at the center of LP. Any other question? Yes, sir. Delta will be delta P. Yes, delta may be delta P, delta may be delta Y, delta may be delta U, depending on where you are considering the displacement and at what load condition you are considering. I have not yet said what will be delta. We will come to that. Okay. Yes.
Is there any reason to consider only that position is in that not to consider the
Okay, because this you have already considered in the triangle.
We are not considering in triangle.
So this additional only I am considering.
If we are not considered this in triangle,
Then you can consider full, but then LP will change. Then LP will not remain same now. Because we are considering moment. So if you increase area here, this will contribute a lot in the moment here. Same increase in the area here will have much less moment. Okay, so this is important that whether you are considering up to here or here. Why we have done this? Because this we are representing by phi y and this we are representing by phi p. So we want to take this dimension equal to phi p and then this dimension as LP. And phi p is fixed. Phi p is coming from the moment curvature diagram. LP we are adjusting in such a way that the total displacement which I am getting at the tip remains. And phi p is nothing but phi u minus phi y. So if I have to calculate delta u, this is our plastic hinge. So there will be a rotation and then there will be a deformation. This is our delta. Okay, this much which is occurring because of the plastic hinge rotation, that we can call delta P, and this much because here it is just reaching my. Okay, so this we can call delta y. You agree? This will be equal to delta y.
So first we yielding place, then we over section go to the plastic range.
Let's reverse it. If I apply this, what will happen? The moment will be like this. So up till this point, I am assuming that it remains elastic.
Yes, sir.
So in elastic beam, how the deformation will occur? Same way as we have seen earlier. So I have applied QU, but I am considering only here. So here it will be delta y. And because QU is more than my, so here the moment is higher. So what will happen? There will be additional rotation from here. And due to that, this curve will go further down. So this is due to this rotation. Here I have shown in the reverse way. First I have shown the effect of rotation, plastic rotation at the hinge, and then the deformation of this portion. So this portion of the beam we are considering elastic. So in actual beam, as you see here, in actual beam, this much portion which is shown in white, that is elastic. Beyond that, inelasticity occurs. We have simplified it. What simplification we have done? We have assumed whole of the beam as elastic, and all the inelasticity I have lumped at this plastic hinge. Rest of the beam is elastic. All the inelasticity we have lumped into this plastic hinge. And this plastic hinge we have assigned a length equal to LP. And this LP is notional. It is for the purpose of computation only. Physically it does not have any meaning. So can you calculate delta U now? Delta U will be equal to delta Y plus delta P.
So, if you are lumping all the plastic in that empty location, and everything in the elastic, we are considering delta P. We can give the beam is elastic, then we can directly use the elastic formulas.
Yes, but there is a plastic hinge also.
Yes.
And that plastic hinge is also rotating. Suppose your beam is very rigid.
Yes.
Beam is not deforming at all. The elastic deformation of the beam is 0. And there is a plastic hinge, and you apply a load. Will there be deformation?
Yes.
So that deformation you have to consider. Now, because of the flexibility of the beam, it is deforming further.
Yes.
So first, the rotation, whatever rotation has occurred at the plastic hinge, due to that it will deform, and then due to its own flexibility, it deflects further. So both the deflections we have. Because hinge is there. If this hinge was, suppose, one is this where hinge is there, another one is where hinge is not there. Will they be same?
No.
So what is the difference? There will be additional rotation. And if there is additional rotation here, there will be additional deflection. Because when I say elastic, doesn't mean that plasticity is not there. Plasticity is lumped into hinge. So elastic along with hinge. Okay. So is not same as the elastic. Delta y, all of you know, it's very simple. We have just derived m by L square by 3. And how much is delta p? You can also write in terms of phi y, okay? And delta p is theta p into L. Okay? So this you can also write as phi by L square over 3. M upon A is equal to phi plus theta p you can write down as phi p, okay, into LP into L. Actually it will be L minus LP by 2, that I have ignored. Phi p into LP, what is that? Phi p into LP here. That is the area of this rectangular portion. Okay. So area of the rectangular portion, area of curvature diagram is what? Rotation. That rotation taking moment about this point or multiplying by this lever arm, what you are getting? Displacement. So due to this portion, the displacement is phi p LP into L. And due to this triangular portion, we have already derived, it is phi by L square by 3. So you know the curvature diagram. Can you plot Q versus delta now?
एक बार रिपीट कर दीजिए 5 p and 3 12.
Due to the plastic rotation theta p here, okay, this portion, this line is straight. So how much will be the displacement here? Simply theta p into this length, which is L minus LP by 2, which I have taken equal to L because LP is small. So theta p into L is the displacement of the free end of the cantilever because of the plastic rotation, plastic curvature.
So 5 p into LP in the area shaded.
Phi p into LP, how do we calculate it? Suppose, let me take this. Suppose there is a beam and the curvature diagram for this is like this. This is curvature diagram. How can you calculate the displacement here? We don't know, some type of loading is there which is giving us phi only here. I want to calculate the displacement at this point. What I do? First moment of area. So what is the first moment of area? This is LP. This is phi p. And this is L. So you can see that delta p is phi p, LP, L, which you can also say theta p into L. So Q delta curve will also be a curvilinear function. Okay, we can represent this also by equivalent bilinear. How? Up to this it is delta y, and beyond that it is delta u, and this is delta p. value of delta u, delta y, I have already given you how to calculate. So we calculate now the ductility of the member of the cantilever beam. Which we also call displacement ductility. Okay, and displacement ductility mu delta, and that is delta u over delta y. We can say that as delta y plus delta p divided by delta y. That is 1 plus delta p over delta y. You can write that as you can write that as 1 plus phi p lp into L divided by phi by L square by 3. So one L will cancel out. So this L I can cancel out with this square. So that is equal to 1 plus 3 phi p lp over the relationship between phi y and phi p and epsilon y and epsilon p we have already obtained. You remember? So from strain ductility we can calculate curvature ductility. From curvature ductility we can calculate displacement. Okay. And this cantilever, this is our simplest structure possible. So a very simple structure, cantilever, we have calculated the displacement ductility if we know the stress strain curve of the material. If we know the strain ductility, okay, we can calculate displacement ductility of this simple structure. So in next process when we will meet, we will move to more complex structure. How we can go to more complex structure? What next complex structure comes to your mind? Cantilever is the simplest. Simply supported or fixed end. Okay. Then beyond fixed end, frame. Okay. So we will see how we can obtain, how we can extend this. If we know the displacement ductility of a cantilever, how we can extend it to a beam, okay, with fixed end or release and frame. That is the next part. Okay, so I think now you can complete the full tutorial. Sorry, up to question number 3. Question number 4, I have yet to tell. And question number 5 also. Only thing is question number 4 is remaining. That I have to tell. How to find it? LP. Okay, yes. Everything you know, but I have not told you LP. How to obtain LP. Okay. So LP comes from experiment. So what people have done, they have tested a large number of cantilever columns and beams. They have calculated the displacement, and from that displacement they have back calculated LP. Okay, which value of LP is giving us the correct displacement? Alternatively, what they would have done, you need to plot the full shape of the curvature. Okay, and then you need to calculate the equivalent value of LP. But measuring curvature is very difficult. You have seen when we are doing the experiment, you can measure displacement at one point, but if you want to measure the displacement along the whole length, it is difficult. Now it is possible with techniques like DIC, okay, where we can measure the displacement along the whole length, perhaps we can get curvature. Okay, but measurement of curvature is very difficult using conventional instruments. So what they have done, they have calculated the total displacement. They calculated the yield displacement and they measured the total displacement. And then they back calculated LP in such a way that you are getting the correct value of displacement. And then they have given some relationships or what we call models. So number of models for LP are available in different books you can find. A very simple estimate for LP is D is depth of the beam. So approximately it is equal to half of the depth of the beam. It's applicable for column as well. Minimum dimension or the dimension in which you are bending. Because if you have a column can bend in this direction also, in this direction also. When it is bending in this direction, then this will be D. When it is bending in this direction, this will be D. Okay, there are other models also. You can look in the book by Priestley. I have already given you. So in the book by Priestley, you can look at it. Okay. So today we will stop here, and when will we meet now? Tuesday. Tomorrow is holiday, 26th January. Then Monday, of course, we will meet on Tuesday. So when we meet on Tuesday, we will revise up to this. I told you in the beginning of today's class, this is the most important portion. If you have understood this, then only you will be able to understand nonlinear behavior of structure. So please be very clear about this portion. You read. If you want to see the video, you can see it again. We are providing the video. See it again, but be very clear, and you can read the books also. Okay, Priestley's book. All this is explained in Priestley's book. Whatever I have shown here, everything is from Priestley's book. Okay. So you can read Priestley's book.